So far, we were dealing with only discrete basis. Discrete basis. Discrete basis means that the total number of basis vectors are finite. So total number of basis vectors are finite. For example, case of spin of an electron. We will see later in more detail spin of an electron. We know that it can take only two states, that is plus 1 by 2 and or minus 1 by 2. So these are two spin states. So there are only two states, and so there is only two basis vectors. Okay, and in this case there are only two basis vectors. Then psi can be expressed as some constant into one basis vector phi1 plus some constant into another constant into phi2. So there will be uh, only finite number of terms in the expansion of this abstract vector psi. That is discrete basis. In that case, we can represent psi in terms of a matrix, psi in terms of a column vector, and operators in terms of a matrix, etc. So that we have learned already. But in some cases, this is not possible because, for example, position of a particle. We know that for every physical quantity there is a corresponding operator, Hermitian operator, and this position uh, can take any values from minus infinity to plus infinity, right? So in the case of spin, there is only two values, plus half or minus half. But in the case of position, there are infinitely many values, and also it is continuous. Continuous in the sense that, consider an example of 1D, one dimension particle in one dimension, and if I take a range 1 to 2, particle can be anywhere in between 1 and 2, and there are infinitely many uh, points between 1 and 2. It is uncountably infinite. So that means it is continuous. The points are continuous. So we cannot represent it using a discrete basis. Means we cannot represent it using uh, a linear combination of finite number of basis vectors. So we need some generalization, and that is known as continuous basis. Continuous basis. This is not only for position, uh, but also for any continuous variable. For example, another important continuous variable is momentum. Momentum, which is represented as p cap. Momentum is also a continuous variable. Momentum can take values from minus infinity to infinity, etc. Okay. And then now what we have to do is we have to convert everything that we have learned in discrete basis into the case of continuous basis. So the two fundamental relations we learned in discrete basis is orthonormality of basis vector, that is phi I, phi j is equal to delta ij, and summation over outer product of basis vector with itself is I. Okay. So these are the two basic relations we learned in discrete basis. With the help of these two relations, we can mm, we can get the matrix representation and do many things. We can insert this identity uh, somewhere, and we can expand it, and we can expand it to inner products, or we can change it to operators, etc. We can do many manipulations if we know these two relations. So we need a analogous relation in continuous case. So now I am writing it for uh, possession basis, where here the index I and j represents that these basis vectors are different. So I need to choose here it is continuous, because uh, so I need to choose different variable. Instead of index, I need a new variable itself. So inner product of x with y is, here it is chronicle data. The continuous counterpart of that is Dirac delta function, delta of x minus y. Okay, this delta function you have already learned in mathematical physics. So similarly here, uh, summation in continuous case becomes integral x with x dx is equal to I. So these two are the continuous counterpart of this discrete equations. Similarly, this is for position basis. I can also write the similar equation for momentum basis also. P inner product with another P is equal to uh, delta of P minus P dash. Also integral of P outer product with P dP is equal to I. So these are the continuous counterparts. So if we know these two relations, we can almost do anything we want. For example, in the discrete case, we were uh, expanding this vector using the basis vectors phi I. So how we got this relation? First we took psi and then multiplied it with I. Then we substituted that I, sigma I, phi I, phi I substituted. Then this psi I written here, and this is an inner product. I am just calling this as alpha I. Then I will get the expression sigma I, alpha I, phi I. Okay. Here alpha I is the matrix element, or the element of column vector of psi, and it is given by inner product of phi I with psi. Okay. Similar thing we can do here also. We can take the basis vector, the abstract vector, and multiply it with I. Then substitute the relation d by dx psi, and this is an inner product, but there is one slight change here, because uh, x is continuous here. X is continuous, and when we change x, the value of this inner product changes, and the change is continuous. So what is a quantity that we know? uh, some quantity that changes continuously with a variable. So that's a function. So this is a function of x, and I am writing this as psi of x. Psi of x. So can represent this vector as integral uh, dx psi of x psi of x. So similar to in discrete case, here alpha was an expansion coefficient for this abstract vector using basis vector. Here also this psi of x, this function of x is an expansion coefficient when we expand this abstract vector in continuous basis. Okay. And there's a name for this function, and this function is known as the wave function in position basis. Is in position basis. Similar thing we can do using momentum basis. Then we will get another function which is also a wave function, but the basis is different. Wave function in momentum basis. Momentum basis. Okay. So what is a wave function? Wave function is nothing but an expansion coefficient of an abstract vector in continuous basis. Right. And similar to the discrete case, a vector can be represented as a column vector. In the continuous case, a vector can be represented using a wave function, which means that whatever information is contained in this abstract vector, which is also is contained in the wave function. Here in discrete case also, whatever information is contained in this abstract vector is contained in this column vector also. Okay. Then we can find out the form of inner product in continuous basis. In discrete case it was like this: inner product of some vector with another vector was the multiplication of dual of that vector, dual with the vector itself, with the another vector. So inner product is a vector multiplication of a vector with dual of another vector. Okay, so that is the inner product in discrete case. So what is the inner product in continuous case? So inner product of one vector with itself, another vector. What we can do is we can insert an identity operator here. Then this will become identity psi, and if I substitute the identity, it will become phi integral dx x outer product with x psi, right? And if I take the integral outside, integral dx, then I will get two uh, inner product. One is phi with x and other one is x with psi. We already know this is wave function psi of x, but here the order changed. It is not the inner product of x with phi, but it is phi with x, and we know the property of inner product that this is the complex conjugate of x with phi. So this is just another function phi of x but complex conjugated. So inner product of phi with psi is just the integral phi star of x psi of x. Okay. So now we know that there are two kinds of wave function that is possible. That is one in momentum representation, position representation, and other is in momentum representation. And there is a relation between these two wave functions, and each wave function contains all the information about about the state of the system. So there must be some relation between uh, two, some transformation that can take uh, from one basis to another basis. Okay, relation between psi of x and psi of p. We know that psi of x is the inner product of x with psi. I am inserting an identity operator here, then it will become psi I x I psi, and I am substituting I in terms of momentum vectors. This will become integral dp p outer product with p psi. This kind of trick is always done using bracket algebra. So learn this carefully, and you must able to do this kind of uh, calculations. It is inserting an identity operator somewhere and substituting the completeness relation and manipulating the resultant equations. Okay, so I am taking the integral outside, then I will get x with p and p with psi. P with psi is nothing but phi of p, and this is psi of x. So there is a relation between psi of x and psi of p. Similarly, phi of p is equal to inner product of p with psi. If I insert an identity here and substitute it using x position representation, then I will get p integral dx x x psi, and if I take the integral outside, integral dx p x psi, and this is nothing but integral dx p x psi of x. So we got the relation between psi of x and phi of p, and phi of p and psi of x. And here you can see this is an inner product. This is also a function. This is also a function, but the this one is the this inner product of p with x is the complex conjugate of inner product of x with p. So we obtain the relation between psi of x and phi of p, and phi of p and psi of x. Both the relations contain another function, and each relation each relation, the complex conjugate of that particular function uh, is present. So what is this function, comma p? And if we notice it carefully, this relation is in the form of Fourier transform. Fourier transform and inverse Fourier transform. So uh, noting this expression as Fourier transform, we can say that this x with p inner product is e raised to ipx by h cross, because that is the function in Fourier transform. And this h cross is coming because the exponent of e should be dimensionless, and h cross has the dimension of p and x, and it is known as Planck's constant. And as a convention of Fourier transform, I am introducing a constant also, 2 pi h cross. So this is just a convention, this constant. And then this p with x will become just e raised to minus the complex conjugate of this e raised to minus px by h cross square root of 2 pi h cross. Then the relation between position and momentum wave functions will become psi of x is equal to 1 by 2 pi h cross integral minus infinity to infinity uh, e raised to plus ipx by h cross into phi of p dp. Also phi of p is 1 by square root of 2 pi h cross. These constants 1 by 2 pi h cross is just a convention. There are many conventions in Fourier transforms, many different conventions. So these are the relation. These are Fourier transforms. And so we defined x with p as e raised to I px by h cross by square root of 2 pi h cross. And what is this quantity actually? Inner product of x with p. We know that the inner product of x with psi is psi of x, which is the position representation of vector set. So this psi of x, this wave function psi of x is the position representation of wave function, wave vector psi. So similarly, what is this? This is the position representation of momentum vector p. Okay, and we know that for every physical quantity there is a corresponding Hermitian operator, and let p be the Hermitian operator for momentum, and assume that it satisfies an eigenvalue equation like this. Operator momentum operating on eigenvector p gives an eigenvalue p and eigenvector p. What is the corresponding position representation of this? Position representation will be p in x basis. This is not p in x direction, it is just basis. I am just getting like this, or let me write like this, p in x basis, and we need the position representation of this p, that is x inner product with p. I am just calling it as f of p. It's just a function. F of p is p. P is just a number, eigenvalue. So this is the position representation of this equation. Position representation, and we know f of p is equal to e raised to minus e raised to ipx by h cross. So if we just substitute it here, that the position representation of p e raised to ipx by h cross, and this 1 by square root, that will cancel from both sides. So we will get an equation like this. Okay, that is some position representation of momentum operator operating on this function gives p multiplied with the same function. So what is this? So easily we can see that it is just a differentiation. If we differentiate this function, the functions will remain same, but one ip by h cross comes down, but we have to somehow cancel that I and h cross. Then the form of p will be minus ih cross d by dx. Here d by dx, if we take d by dx, this I, p and h cross comes here, but in order to cancel I am just multiplying it with minus I. In order to cancel 1 by h cross, multiplying with h cross. So this is the position representation of momentum operator. Momentum in one dimension. In three dimension, this is minus ih cross dou by dou x I cap plus dou by dou y j cap plus dou by dou z k cap. So this is the position representation of momentum operator. So the position representation of position operator is just x. There is no difference. Similarly, we can have the reverse, where we can have the momentum representation of position operator, which is ih cross d by dp, and momentum representation of momentum operator. This is momentum representation of position operator. Note that there is no minus sign here, and this is just px, p in x component, the x component of the momentum. In three dimension, this will become three dimension x ih cross dou by dou px. This is x component of momentum I plus dou by dou py j cap plus dou by dou pz cap. Okay, so now we successfully transformed everything we know in discrete basis to continuous basis. So we transformed Chronicle delta to Dirac delta, summation to integration, and uh, the row vector in discrete basis is equivalent to wave function in continuous basis. Inner product, inner product in discrete basis is multiplication of a row vector and column vector. Here it is integration of two functions, and also in discrete basis operator is represented by a matrix. Here an operator is represented by a differential operator. Okay. Here this is just a differentiation. Okay. So we can break here, and we will do problems in the next class.